This is the fourth lecture of the takeoff performance. And in this lecture, we will learn how to estimate the airborne distance, which is part of the takeoff distance that is from the liftoff point when the aircraft lifts off until the screen height is reached. So we can see the takeoff distance is comprised of the ground run distance plus the airborne distance to screen height. And in this mini lecture, we will learn how to estimate the airborne distance to screen height. So before we learn how to do the calculate the distance, first let's figure out what is excessive power. And in order to determine the excessive power, we need to place the assumption of small angle of attack assumption. So on the right hand side, um, we have the aircraft is being lifted off towards screen height. Okay, so that's equation along the flight path. So we have thrust, drag, and also there is a component contribution from the weight of the aircraft. Okay, so the right hand side are the forces and the left hand side of the equation is the acceleration. And okay, on the direction normal to the flight path, so we have the mass times the acceleration. And on the right hand side, we have the lift and also a contribution from the weight, that's W times cosine theta. And this theta is a flight pitch angle. Okay, so we define the rate of climb Vc is dh over dt. Basically, that's the vertical speed of the aircraft. And we can see Vc, the relation on the right hand corner, top right corner. So Vc is a component of the airspeed V. Okay, so then we can have Vc equals V times sine theta. Theta is a flight path angle and equals dh over dt. Okay, and now we are rewriting the first equation in the group above, and that's along second law along the flight path, and you can see the sine theta is highlighted. Okay, so what we are going to do is write down sine theta explicitly. So on the right hand side, it's just a conversion of the equation. Okay, so now combine these two equations, we can determine Vc. Vc equals dh over dt equals V times something in the bracket. Let's walk further. Now we can define the excessive power, which is V times T minus D. T minus D is like excessive force, and then power is force times the velocity. Okay, and on the right hand side, basically that's just a rewrite of the above equation. Vc equals something. Yeah. Okay. And then we just reorganize the equation on especially the second term on the right hand side, v times dv over dt. So we can rewrite it half dv square divided by dt. Okay, so further we rewrite the equation, reorganize it, and finally we can have the weight specific excessive power. Just now was excessive power, so weight specific excessive power is V times T minus D divided by W, that's a weight, and then we can have the PS. In the previous slide, we determined the excessive power and the weight specific excessive power. Now we will define the excessive energy and learn how to estimate the airborne distance SA, which is the objective of this mini lecture. If we move our eyes to the bottom of the slide, we can see the aircraft is lifting off from the liftoff point until the screen height. SA is the airborne distance. And we know thrust being greater than the drag is used to increase the kinetic energy and the potential energy. And that means in the form of greater airspeed and altitude. So the kinetic energy will increase as well as the potential energy. The kinetic energy increases in the form of greater airspeed, and the potential energy increases in the form of the larger altitude, increasing altitude. Okay, so that's the energy conservation equation, delta E, that's the energy increase. And we have the kinetic energy and the potential energy at the screen height minus the kinetic energy and the potential energy at the liftoff point. So that's the energy difference and delta E. Okay, so now let's write the EK and EP respectively at the screen height and the liftoff point. And then we just combine the kinetic energy together and the potential energy together. Kinetic energy is half m times v squared, and kinetic energy is mg times h. Okay, so we're replacing m by w over g and mg by w. So the mass is replaced by weight. And also we know delta E equals T minus D, which is excessive um, force times SA. And so that's excessive force times distance the aircraft traveled. And we have the work. And you can see it's highlighted as this is an estimation because T minus D is not exactly in the same direction as SA because there is a flight angle theta. So the flight path is tilted from the ground. But we assume, as I said in the beginning, we assume the pitch angle is a small angle. So delta E can be approximated by T minus D bracket times SA. Okay, so now we are equating delta E in the form of energy and delta E in the form of excessive force. So we can have this new equation by equating the above two equations. Okay, so then we can write down SA equals W divided by T minus D, and then that's the kinetic energy and also the potential energy. And if we know all these parameters, we can estimate the airborne distance for the aircraft. Okay, so we know how to estimate the airborne distance as A using the equation highlighted in here. So now we can use this equation to estimate, to work out an example. So let's see the question. The same commercial aircraft, twin turbofan transport aircraft, which we have dealt with this aircraft before. So it has a parameter like below. So at V liftoff, at the liftoff point, and the thrust per engine is 260.75 kilonewton, and at screen height, which is V2, it's reduced a little bit, the thrust. It becomes 203.42 kilonewton. And also we can see the liftoff is 145 knot, and at screen height is 161 knot. The drag, let's look at the drag CDP and the CDI, parasitic drag coefficient and induced drag coefficient, also changed slightly. The parasitic drag coefficient doesn't change, but the parasitic drag coefficient does increase a little bit, and also the takeoff weight doesn't change, and the wing area apparently doesn't change. Okay, so we need to use this SA relation to estimate the airborne distance. And having a brief look at this relation SA, and we know the W, which is M times G. We know the thrust, but there are two thrusts. So one thrust is at liftoff, the other thrust is at the screen height, and also the same for the drag also changes. And we know the height, we know the speed at liftoff and the screen height. So the tricky point is how which thrust and which D we should use. That's highlighting here in green circle. And T and D at liftoff and screen height has different values. We can use an average value to estimate the airborne distance SA. Okay, we've analyzed the question a little bit, and let's see how we can work it out. And as we said just now, we can use averaged thrust and average drag. So let's work out the thrust first. Okay, so we just average the thrust at the beginning and at the liftoff and at the screen height. So, and then the thrust, average thrust is 410.17 kilonewton. And the drag, so we need to first estimate or calculate the drag at the liftoff. And since the drag has two components, the parasitic drag and induced drag, we need to plus them together. And because the drag coefficient, we need to times half rho v square, and the v velocity should use the liftoff speed. And the same for the drag at screen height. So we need to use V2 and also the CDP and the CDI at screen height. So for drag at liftoff, it is 62.911 kilonewton, and the drag at H2 screen height increased significantly. That's 263.8 kilonewton. And then we do the average as agreed before. So the average drag is 163.36 kilonewton. And finally, we can estimate the airborne distance as 534 meter.